VU Amsterdam.
Vrije Universiteit Amsterdam, starting just last September in 2023. He works on a variety of different topics in the field of robot learning, but primarily focuses on deep reinforcement learning. And he is particularly interested in the combination of deep RL with evolutionary principles and for the development of AI-assisted design methods and physical embodied intelligence. And prior to that, he was a postdoc at Aalto University and the Finnish Center for Artificial Intelligence in Espoo, Helsinki, Finland. And he's worked for other places like the University of Edinburgh, Google DeepMind, Facebook AI Research, and TU Darmstadt with Jan Peters. So otherwise, the floor is yours, and go ahead.
Cool, wonderful. And thank you so much for the invitation and a very good introduction. And I hope you can hear.
It's like, let me stop talking.
Okay, good. I give you like a second. Good, cool. I hope you can hear me. If there's anything, then just let me know during the talk because I don't see anything anymore. And thanks so much for the invitation and also like the very cool introduction. So originally, when I started preparing this talk, actually, it had like the title Reinforcement Learning Perspective. But actually, I decided later to actually change it to like a robot learning perspective because some of the problems I'm going to talk about today is not only like learning specific, but specifically also looks from the robot learning or like the robotics perspective. So we're going to talk about some challenges as well, actually, in the topic area of co-adaptation. I got already like a very good introduction, so actually I don't have to say very much on the slide. So I have been around a lot, which makes introductions like a little bit tricky always. But my main topic areas are basically like reinforcement learning. So I would say I am interested in applying reinforcement learning and deep reinforcement learning to problems relevant to the real world, so real world robotics. But as said, like one of my special topics at heart is basically how can we co-design robots, which today's talk is about. So there's always like a very good motivation, of course, for the research we are doing. So for me, it actually started way back in 2017 with this paper which we had on robotic science and systems, actually, which was about how we can bring learning algorithms from the laboratory outside into the environment, really, into the field. And specifically, actually, this research was about the desert environment. So we were interested or like collaborating actually with a design and manufacturing professor who was really into these origami robots. So basically robots which are made from paper. So imagine you have like a two-dimensional sheet and then you laser cut it very smartly and design it very smartly. And then you just pop it out of a 2D material and put in your motors and sensors and then you have a robot. And the idea was really to investigate the locomotion styles of sea turtles with this robot, because the idea was like with this really cheaply manufactured robots, you can actually go out into a sand environment where you would normally not like to put your robot for very obvious reasons that you do not want to get the sand into the gears of your robot and have to buy a new 50,000 euro or like dollar expensive robot again. This meant also for this research project actually that we had to manufacture these robots ourselves. And back then I was a PhD student. I had like really nice collaborators who were also PhD students. So we came up with this really nice pipeline actually on how to design these robots, right? So we had like a relatively simple production process. So like there was some 2D cut design actually, a little bit 3D as well. Then mostly using laser cutting, which is a fast manufacturing method, but it took us still like a couple hours to actually produce the robot prototype. So you see like a sped up version actually here on the left side. And one of the problems we actually ran into is that, especially because this manufacturing lab was at a different point of the university, so it was in one of these satellite campuses, we had to go there first for like 1 or 2 hours actually. Like it took us 1 or 2 hours by bus ride actually to get there. And then actually manufacturing was, even though it was relatively fast, it still took a couple of hours. And of course, the main problem is like, especially with these designs, is that of course the first prototypes did not really work out. So we had to go in, redesign, or like design the robots, print it, actually manufacture it, test it outside in the lab, and then actually rinse and repeat this process. So actually like the most time it took was actually to design this robot. And this was actually which sparked this idea. Hey, could we actually not only apply reinforcement learning to the robot, so not only learn the behavior, but can we actually also use AI technology to, or like learning algorithms to actually help us design this robot? So this sparked basically my interest in this topic, even though the paper itself was actually already like pretty cool to do. So if you talk about co-adaptation of behavior morphology, we often actually talk about these two loops, right? So we have like on the left side, you see like I say, of course, a reinforcement learning loop, but you can also say it's a behavior learning loop. So given a robot, we actually want to find some sort of behavior. Historically, like a lot of people have been using evolutionary algorithms here, but nowadays, of course, we use deep learning and reinforcement learning for that. And then on the right side, we have, of course, like the design optimization loop. So given the robot embodiments, which we tried out, we want to collect the data about how well they perform. And given the data, using some machine learning algorithm, we want to make predictions, which design variables we need to change in order to improve the performance, and then have to go through the costly manufacturing process. Often, so this will become a little bit relevant later again, we actually aim to, or like we have some function of the robot in mind. So for example, like locomotion. So we always work normally with an objective function, which is given by a human, of course. So if you look at from the reinforcement learning perspective, what we are talking about actually, I call it the multi-embodiment or multi-body Markov decision process. But if we are like very, very accurate, actually, it's like a type of contextual Markov decision process. So the context here is really the context here is really like the design variable C. So the agent morphologies, which then transform actually the objective which we normally have in reinforcement learning. So everyone of you probably knows the discounted cumulative reward is what we are trying to optimize, given our policy and our transition probabilities. So the important difference is if we consider actually adapting not only the policy, but if we want to change actually the design of the robot, then we introduce basically changes to 3 of the functions. So we not only, of course, change the reward function, right? The embodiment may play a role in the reward function. So if you think about cost of manufacturing, or if your reward function itself actually in some way uses the transition function, but also we actually introduce changes to the transition function and the initial state distributions, right? So every time we basically experience a new embodiment, we basically have a distributional shift in these distributions, and then we get a new form, or like the probability of what the next state is impacted by the change of our morphology, which is intuitively very, intuitive. So if you change the length of the legs, of course, if you try to, let's say, if you're in the middle of it, or like starting to jump, the length of the legs, of course, influence at which position you will be in the next time step. Of course, we not. Sorry, was there
a question? Yeah, real quick question. Should the reward function also be, if you can hear me okay?
Yeah.
Should the reward function also be conditioned on
actually
these parameters? Because you want a design that's independent of morphology, but now you're conditioning on that morphology. How does that affect the reward function?
Good question. So technically, if you want to keep this process as broad as possible, it can be part of the reward function, right? You could take into account that, for example, that like you consider a certain manufacturing cost, right? So for example, the type of material or the number of materials you use, and this is then of course like a static component you add to the reward function. But then also sometimes, because technically the reward function is the state, the action, and the next state, you could somehow make the reward dependent on the transition function. For example, if you want actually to use st+1, right? And then technically the reward is part of it. So it's like more, it can be, but it doesn't have to be, right?
Mm-hmm.
Yeah,
that sounds good.
Sorry, can you hear me?
Yes, I can hear you.
Oh yeah, okay. So in this formulation, we're assuming that the state and action space is shared across the different morphologies?
Yes, we do. Yeah. So like normally what I assume is like an action space of R, right? Like R to the power of something, like to the number of actions or the number of states. In principle, if you want to make the action and state spaces dependent on the morphology, then of course, like this would also be a function in itself, right? So you're thinking, for example, if we actually change the modularity of the robot, right? If we attach new motors to it, then the state space changes, and then of course, like the S and A here actually should be functions, right? So they should take in the morphology parameter, and then actually map to a state and action space, right?
Okay, thanks.
Yeah, but this is, okay, maybe to clarify, so this is the simpler version, right? So we basically assume we have design parameters, but in this setting, actually, we do not consider changes to the action and state spaces. But you're right. So if you talk about graph neural networks, for example, or like graphs of robots, or you're changing the UIDFs, then actually you will have to change it, like extend it a bit more.
Yeah, sounds good. Let's chat more later.
Good. I have also like one slide actually where I talk about GNNs, but it comes a little bit later. Cool. Okay, so then of course, like also the policy may be parameterized on the design variable, right? And here we actually have like two different choices which we can have in principle. So of course, like the most broad definition would be to always make the design variable actually part of the policy, but we can roughly differentiate between two different styles. So we can have the embodiment aware policy. So basically the policy knows the embodiment, the policy has to exploit the embodiment. And this we actually often use for transfer learning or for optimal control. So the hope is basically you train this policy on a lot of designs, you move to a new design, and you basically hope that the policy can somehow like a little bit generalize and then give you already like a good estimate of which actions you have to execute on this morphology. On the other hand, we also actually want a policy to really take the embodiment into account and like exploit the embodiment, right? So like if you change, for example, like the length of the legs, the policy should know about that and should propose actions which actually are interesting for that. On the other hand, then there's like, of course, the agnostic policy variation, where basically we try to learn a policy which can be applied across a lot of morphologies, and by basically forcing the policy to not take the embodiment explicitly into account. Of course, you can also make the embodiment aware policy or force it to basically have the same features. But normally you will then not actually add the embodiment variable here. Again, like if you talk about graph neural networks, it's like a different story again. And here actually we are more interested in robust control. So we're actually interested in learning a policy which can be, or which is robust to the embodiment or embodiment changes. So for example, if you produce robots, you would introduce manufacturing errors, so not all the robots are the same. In that case, you actually want to have an embodiment agnostic policy. Good. Okay, so co-adaptation. So co-adaptation, if you look at it again, like from an optimization problem, it's basically like a bi-level optimization problem, right? So we have an inner and an outer optimization loop. In the inner optimization, we are actually interested in learning the behavior. So basically doing our reinforcement learning or finding a policy. And then in the outer optimization loop, actually, we are interested in changing the design. The reason we have this structure in there, so that we, for example, don't switch around the maximizations, is actually that we are operating on different time scales in the two different levels. So we have in the lower level, we have, of course, the behavior optimization. So we are looking at trajectories, right, of episodes. Usually, the embodiment is static during this time. There's again like a caveat that I know that there's like one robot, you know, if you think of a robot which can change its changes, then it's like a different story. But for the purpose of this talk, we assume the embodiment is static. So we are trying to actually optimize our policy given the data we collected. We are then trying to use some learning technique actually, which can be reinforcement learning, supervised learning, etc. Then actually we try to optimize our morphology parameters. And then if we have found a new morphology, we iteratively repeat the whole process again. So looking at the computational costs, so like some comments here again, is that actually computational costs on the behavior level is actually rather high, right? So in the behavior learning level, we're actually interested in robotics really to learn policies quickly, so with the least amount of data. And also we are interested in fast inference, right? So we want our policy to be near real-time evaluate, like be able to actually propose actions in real time such that we can actually solve like locomotion problems or any task basically which requires or is highly dynamic actually, high reaction times. Yes, so basically like we want to fail fast and learn fast, okay? On the other hand, if you look though on the design level, I would argue, and this is something which is maybe like, again, like not many people would maybe consider that or agree with that, it's actually that the computation cost is rather low, right, on the design level. So what I mean by that is actually that the manufacturing processes which we are using, and I'm not sure if you can see that with the bar here, but the manufacturing processes actually are relatively slow, right? So this may actually be the word which is covered up here. So if you manufacture a robot, even if you use laser cutting, it takes several hours actually to produce the robot. If we do 3D printing, even though we are saying, okay, 3D printing is fast and everything, 3D printing actually also takes several hours. So it usually takes like, on larger robots, actually up to 8 hours. Again, the larger the robot becomes, the larger the manufacturing times usually become. And this means actually that computational cost is actually not even that important on the behavior optimization level anymore. Like if an optimization of a design takes us 50 minutes versus 1 hour, in the grand scheme of things, it doesn't really matter to a roboticist, right? Because if you just let your computer run for 1 hour and then the manufacturing process actually takes 10 hours, then the 1 hour is like a very small amount of the whole manufacturing process. Good. So today I want to talk about 3 of the core challenges which we actually have in the field of co-adaptation, specifically in robotics. The first one is really that adapting behavior design and simulation leads to the problem that the agent often exploits its simulation environment and not necessarily the real world. So like if you work in robotics, then of course what you know immediately what I'm talking about. So basically the simulation tree idea. The second is already what I said, is basically manufacturing cost outweighs considerably the computational cost on the design level. So massive evaluation of design candidates is not possible really in the real world. And then, of course, the last challenge is something which I'm going to talk about the work we did, is basically that, of course, also if you consider the problem of co-adaptation, you really rely on the correctness of the reward or the objective function. Now, if you have done reinforcement learning, you actually know that it's already hard to come up with a good reward function for just behavior learning. Things get a little bit more tricky, actually, even if you consider joint adaptation of behavior design. It's not always obvious how to come up with good objective functions. Good. So let's dive into the first one, where I'm basically talking about some of the work my like some colleagues and other authors did, just to get some intuition what co-adaptation actually is on real robots. So there's like this really nice paper by Lipson. And it's a paper I really like to actually cite because like it's one of the few papers which actually evaluated the simulation tree gap, other than like a recent paper I'm going to talk a bit about later. So in the Simpson paper, basically, they also co-adapted behavior and morphology of a robot on a much simpler level. So they said they used the neural network, but the neural network thing with very, very simple, I think it was even linear layer neural network, which basically just controls like 1 or 2 motors in the robot embodiment. They evolved these robots in a simulator and then actually produced them and evaluated multiple different robot types they found to be optimal in simulation. Now, if you look into the paper, there's actually this very nice table, which basically shows the performance of the design prototype found. So like if you look on the left side, you have the virtual performance. And we can see that the tetrahedron actually is the worst performing prototype, but arrow and pusher basically outperform it by almost twice the speed. However, if we then look at the physical prototypes, the relationship is really inverse, right? So suddenly the robots, which were found to be optimal in simulation and really perform much, much better, are now performing much, much worse, really. And this is like the typical thing you actually expect is that the reinforcement learning algorithm is really exploiting, or like the learning algorithm is exploiting actually the simulation environment and not adapts to the real environments. And although the paper is like a little bit old now, so it's like 24 years old, this simulation TLD gap actually has been shown like several times, especially with non-standard material, like for example, deformable object materials. So David had a really good comparison study actually on that. And then also Josh Bongard had like this sim-to-real gap paper where they showed that even if you optimize something simple like a wing, you still have a non-monotonic simulation TLD gap actually. As a small gimmick, actually, this is the actual size of the prototype, so they were actually really large. I was a little bit surprised when I had it actually in my hand. Yeah. Good. Okay, so I hope now basically I have convinced you that the sim-to-real gap is also real when we do co-adaptation. It's well shown in literature. So it is important for us actually to evolve or like be data efficient and be able to develop algorithms which we can apply to the real world, which comes back to our original problem, namely that the manufacturing cost is like really, really high, right, of our robot prototypes. And the challenge really, what I'm really interested in, even though it's a little bit far-fetched at the moment, but in a perfect world, what we actually want to have is that we have one robot prototype. So we have one robot prototype and one PhD student who is helping us to do the research. And then iteratively over a few design iterations, we basically find an optimal design and behavior for this robot prototype. This is a really hard problem, but it really ties into this data efficiency in order to avoid many of the issues of sim-to-real gap. Even though we may actually also exploit this information. And I think like this challenge or like this problem that actually the more expensive prototypes are in the real world, the less we are able actually to have like a large population of them is often not very well considered in recent papers, which, you know, use simulators, evolve thousands of robots and then show that they can find a good design. Unfortunately, like we don't have like that easy often time in the real world, and especially not in robotics. Cool. Okay, so now we come a little bit to the work we have been doing in the past. So as I mentioned, historically, especially in evolutionary robotics, there was this approach of using a population-based approach, right? So you have a population of robots or design prototypes. You evaluate them, select certain designs, maybe even adapt the behavior at the same time. So there's like a little bit of difference that some evolutionary algorithms don't adapt the behavior. Others actually use reinforcement learning, but in any case, you would usually select one or several prototypes to improve the behavior, collect data, and inform your loop again, right? But this requires, and what like the underlying assumption is basically that you have like access to multiple robots, which we don't necessarily have. Like this robot actually I have in here, I think the cost was 70,000 and plus the person hours, right? So you need usually as many personnel actually to supervise these robots. Good. So the first approach, which we actually presented in 2019 on Core, was basically that we wanted to evaluate, okay, if we do already reinforcement learning, can we actually speed up things? Can we actually exploit the fact that we do apply an actor-critic learning approach to the prototype? Can we actually speed up the design optimization process? And in this first paper, basically what we did, so we had a single design prototype, which we evolved in simulation, right? But we considered the simulation really as a stand-in for the real world, just to make my life as a PhD student a bit easier at the time. So we evolved always only, or evaluated only a single simulation at the time. What we will do is actually collect data on the prototype, improve, of course, our policy, but then what we would actually end up with is like enough data to train a second set of networks, so like a policy and a Q network, a critic network, which was trained on all of the data of all the prototypes we have seen up to that point. And what we then actually would be getting is like a critic function, which we can query now for different design variables. So like the design variable was really part of the information we gave to the critic and to the policy. And using the critic, what we were doing actually is to optimize now for the design parameters of the robot, which was in the case of Hive Cheetah, for example, the length of the leg elements. And then the cool thing what you can actually do is, like, as you know, neural networks are really fast to do inference on, so like you can query them really quickly. And it turns out actually that within 50 minutes, we were able to evaluate, like, I think the numbers were roughly 150,000 design prototypes, versus if you would use a simulator, I think we were able to, in roughly the same time, evaluate, I think 5,000 or something like that. So like you really get a much higher throughput. And the question really was, can we use the Q function as a surrogate function, basically? And then here are the results, right? So like basically we were able to show that, okay, over 50 design prototypes, we can outperform the classical approach, which is here blue. So the blue approach would be the classical evolutionary approach with reinforcement learning thrown in. And then the red line is basically our co-adaptation approach, really exploiting reinforcement learning on both levels of the design and the behavior learning process. And the cool thing is really that here we plot against the number of design prototypes produced, right? So you see here the best performance of each of the designs produced. But if we plot this against the number of iterations or trials in simulation, then we can really see that we were able to increase the data efficiency, because the classical evolutionary approach, which uses the simulator to actually evaluate the performance of the design, really needs many, many more simulations and real-world experiments if you were to do it in the world. Is there a question? Because I hear the... No.
I mean, I'll ask a question.
Okay, good. Yeah.
It's like ruminating sound.
Yeah, no. On the last slide, you were showing you were using the Q function to help. Was that to help filter some of the like suggestions that you've designed already?
Yeah.
Like before training a full policy. So how does that work? You get some expectation.
Okay. Yeah.
Policy independent
Okay.
of...
So the answer to that question is like very long, actually, because like the slide is relatively simple, because otherwise I'm super running out of time. So there are like a lot of tricks, actually. So the expectation here is actually over the initial state distribution. We, of course, don't have access to an initial state distribution, or I assume we don't have access, right? Because otherwise there's no point when we query the simulator all the time. So instead, what we actually use is we have a special replay buffer in which we store all the initial states seen, and then we take basically like a batch of it to evaluate this expectation, right? So we have an expectation also in regard to the state. So this is not shown here as a detail. And then we also query the policy actually for an proposed action given an initial state and the design we actually want to query for, right? So the query actually of the design goes into both the Q function and the policy here. And then, like I said, so we have these two sets of networks, right? So we have basically policies and Q functions which train on a global level, so sort of like meta-learning, think meta-learning maybe. And then if we go to a design prototype, then we actually train a policy and critic to really overfit to the current design prototype and have basically, I think like it was a mix of 90 to 10%. So 90% of the data comes really from the current design prototype, 10% comes from all of the other prototypes. And this trick was really just like to prevent collapse of the networks, right? Because otherwise we have a stark distributional shift to suddenly batches of only one prototype. Yeah.
Okay.
I'm happy to answer more questions, but maybe we do it at the end of the talk, because like for that part. But is it clear, or?
Yeah, that's better. I mean, this is a really hard thing to do. But yeah, thanks for the details on.
Yeah. Yeah, that's why I don't put it often on the slide, because it would take me actually like 20 minutes, I think, to go into everything. But we can talk about it also at the end of the presentation. Cool. Another cool thing, actually, of course, what you can do. So here on the left side, you see one of the experiments, which I found personally really cool. So we had this walker environment. And actually, my favorite really is because the algorithm figured out that one short leg and one leg longer actually helps when the walker was like falling forward. So it could basically do these loops forward by exploiting the kinematics of the long leg, really. Another cool thing is really that you using the Q function, you can like query basically for the design space, and you get this very cool looking low dimensional plot. So this here is actually a PCA plot, which we did on the design space. So we had, I think for half cheater it was 6 dimensional. So we brought it down with PCA to 2 dimensions, and you get this very nice nonlinear latent embeddings, which you can visualize, of course. Cool. So what I mentioned already in the beginning, right? So far, most of the cases I actually consider the problem of having a fixed design space. So we operate over n dimensions really in R, right? So continuous design optimization. Of course, you can also follow the mixed discrete continuous co-adaptation, where we have one paper actually on arXiv, where you then also optimize the graph structure. So I think you're optimizing the number of motors, right, on your agent. One option, of course, to using that is actually a graph neural network or transformers, or nowadays also like LLMs, of course. So like you have different options, of course, to do that, and then basically transfer the learning paradigms which I presented before really to the setting as well. So it is possible, even though it doesn't make the design problem like much easier, right? So like you now have to optimize over continuous design variables and a graph. So basically you blow up your bi-level optimization problem to like basically like a tree-level optimization problem, if you consider graph optimization or topology optimization separately. Cool. Okay. Let me quickly check the time. Yeah. Now let's come to another paper which we presented actually. So this was really about the problem that it is hard to come up with good reward functions in behavior learning as well as in design learning. And one of the things which irked me a little bit in this first paper, so this is basically the graph showing the optimization loop which we had in the previous presented approach, so this co-adaptation approach, is that, you know, we have AI for optimizing behavior, we have AI or like reinforcement learning for design optimization, but we still have the human in the loop, right? So the human still has to come and be like, this is the objective function which we want to optimize. So perfectly, actually, we want to get rid of the human in the sense that actually we want also to actually get a learning approach to actually extract really a reward function for our learning process. And for that, we actually use adversarial imitation learning. So many are probably of you familiar with imitation learning. So up to that point, imitation learning hadn't really been applied to co-adaptation as far as I know. So this was our goal, and basically we had like two research questions for this research really. The first one was, okay, if we adapt the behavior and the design of the robot, does it really has any benefit, right? Because normally if you do imitation learning, we only change the behavior. So now the question is, if we also allow the agent to change its design, does this lead to any improvement, right? This was not really clear at this point because the embodiment you have could be just enough to basically imitate the task. The second research question, I would say, is more like a challenge. So we really, really wanted to only use a learned reward function. So like a reward function learned from data. And I didn't want to put in any more regularization reward functions, right? So normally in a lot of papers, especially in the space of imitation learning, if you have a robot arm or like a humanoid which learns from demonstration data, sneakily, the papers often introduces actually like regularization via reward functions. For example, think about like stability or like, you know, upright positions, and not everything is really learned from data. And we wanted to actually only learn from data. Good. Okay, so the problem, or like one of the core experiments really, so we have also experiments, I think, on Hive Cheater and Walker, if I remember right, was really like to match the demonstration data provided by a human demonstrator. So we had motion capture data from this famous Carnegie Mellon data set, right? So like a human walking or kicking a ball. And then again, like a simulated humanoid. So many of you are probably familiar with the humanoid task in Machoko. And of course, the main topology and like the forms and elements of the humanoid, they are, you know, inspired by the human, but there's no real good mapping to each of the segments on the human and to the robot. So we had to come up actually with some tricks, especially because we do not have the actions at the joints of the human, right? So what we use actually, we use the motion capture markers and also placed markers actually on the robot. So this is basically one of the limitations of the paper. You would technically have to have a motion capturing system on the real robot. And then we roughly match these markers between the simulated robot and the agent. So then what you can actually do, once you have this feature state space, which we indicate here by the phi, right? So phi of S is basically the motion capture marker. So just keep that in mind, is that you can come up with the state distributions, right? When you have two different state distributions, you have the state distribution of the demonstrator, you have the state distribution of the imitator. So the state distribution of the demonstrator, of course, is fixed because we have the recordings of the human, they will not change. And the state distribution basically tells us how likely is it that we see a certain state within the motion capture data of the human. So now on the imitator side, we actually have a state distribution which is parameterized, right, by the policy. But in our case, we extended it also to be parameterized by the design variable C, right? So here, basically, we have a slight deviation from the normal state distribution, where basically we also depend, of course, on the policy, but we also depend actually on the transition functions, especially on the design. And the goal is really like to have these two state distribution match. What you do for that, of course, is to use the divergence measure. So anything like, for example, a Kyle divergence. And then we just repeat the recipe, which we already introduced earlier, namely we optimize the behavior. Once we have optimized the behavior a bit, we switch over to the morphology optimization. And in each of these steps, we really try to minimize our divergence measure. As already mentioned, like one of the examples, which is really intuitive, is to use the KL divergence really on trying to minimize the mismatch between these two probability distributions. In the paper, again, for the length of the presentation, usually I omitted, we actually used the state alignment-based learning. So the Wasserstein distance was actually used because we found the KL diversions actually didn't work very well in our setup. Good, and looking at the results actually, so here are some of the experiments, and the results were, according to my PhD student, not cherry-picked, so he just randomly basically visualized some of the behaviors he actually collected. On the left side, we see the original motion capture recording, so we have the human running, and then we have like a demo actually, and here you see really the motion capture data where the human is kicking a ball. So we don't see the ball, but just imagine there is a ball actually the human is trying to kick. And then the really cool thing which we are able to find is that if you compare now the standard humanoid, which is the blue one, versus the co-adapted humanoid, we can really see that the co-adapted humanoid really has the same posture and behavior as the actual human. However, if we will just do or repeat the same training process on the standard humanoid, then actually it gets this weird crunched over behavior. And it doesn't really match what the human is showing in the demonstration. Even worse, if we go to this ball kicking demo, then actually what we can see is that even though our humanoid looks really, really funny, right? So with a really short torso, it actually kicks the ball. However, the standard humanoid is basically just getting stuck in the first part of the state distribution probability and is just stamping forward, but never actually executes the kick in this case. So the cool thing is really what we can say here is that, yes, actually adapting the behavior and the design of the robot actually leads to a stark improvement in performance and matching the behavior. And we can actually also show that. So we, as mentioned before, we use actually Wasserstein distances as a divergence measure. And if you evaluate them, actually, you can see that co-adapting the behavior and design at the same time, so the blue line, we actually get a much lower divergence measure than if you would only optimize the behavior, which is here the active green line. So the green line actually gets stuck in these cases. And here you can also see like the theoretical goal. So we basically, this demonstration Wasserstein distance here actually is like the internal Wasserstein distance within the demonstrator set. So we took different editions of the demonstration set and then computed like the internal Wasserstein distance, which is of course not super accurate. So that's actually why you can see here we actually outperformed the measure like a little bit more in the soccer kick. Cool. How am I looking on time? How many more minutes do I have?
And I guess we're going till 12:30, so you have.
Okay, good. Cool, then I still have enough time to go over that. So like we also had this paper actually about model-based co-adaptation, right? So far I have really talked about model-free approaches mostly, where we use model-free reinforcement learning. And then of course the obvious question is, can we apply also model-based reinforcement learning to this problem? And the main idea which we had in this research was really to use like a dreamer or an imagination augmented training approach. So if you know dreamer, basically the ground idea is that you learn a model and you generate synthetic data, and with the synthetic data you try to learn your model-free algorithm such that basically the training progresses much faster. So the idea was really like to learn a dynamics model, use it to hallucinate outcomes of trajectories when we change the design actually. and then generate this data for the model-free reinforcement learning approach. So relatively straightforward. And since I have enough time, actually, I can also go quickly over the learning functions. So the first part is a classical, I think in this case, it was actually the SIC loss. We actually get like a second loss, which is then over the synthetic data set. So we always consider like a mix of real data and synthetic data, or like at the time we did. And here we actually assume that we have a design generator. So some function which, given the design, actually generates us a new design. For example, we're adding Gaussian noise to design variables, or like just uniformly sampling a design. And then we use that actually to hallucinate the outcome of a transition function given the previous state and the action actually. Good. And the good news is, so here's the good part. The good news is, yes, it improves. So on the designs which we have seen. So basically you can see here that the model-based approach like performs like much better than the model-free approach, but there's a big but. So that was actually like the negative result we really reported in this work, is that actually the moment you start deviating from designs you have seen, the learning process really collapses. And we actually were able to see that after like a couple designs, actually the error really accumulated, and like the model-free reinforcement learning approach basically just diverged, and we didn't get any more like good predictions on the next design to execute. So that is basically like the bad result, and I think this was actually something where we have more work to do. Also like to mention, this was especially also considering the low data regime, right? So we only trained over 50, or I think 55 designs actually in total. So something like this would actually work if you consider like a large population, or like mass simulation of different designs, for example. Good. And then actually Maria, so like the PhD student actually who did this, she also like investigated a little bit into the possible causes of this behavior. What we found actually is that if you change the design variables, so these two coordinates here basically represent the changes in design. If you change them, actually you get like a really non-linear behavior in the transition function, which you may actually expect if you sit down and think a little bit about it. So like if you have locomotion, or you do something like jumping, the length of the legs actually impacts, of course, like what happens at the next time step. And you know, the length of the leg actually can be the difference between touching the ground or flying through the air still, right? So if you have like a walking behavior. Good. And actually, since I have a bit more time, I go to the second slide set. So this was actually like a presentation I just gave. So this was about a workshop paper, which we just had out actually. And thinking back about the work which we did on imitation learning and co-design, we actually had also like work with a master's student, Sergio, actually, who investigated, okay, if we have imitation learning in place, can we actually use self-imitation learning to improve the data efficiency? And the setting is basically the same. So we have a market decision process considering different embodiments, so like nothing new here. And the idea is really that, okay, if you do co-adaptation, and especially also in the single design progress, then what we actually end up with is like a trace or like a history of policy and design combinations. And the idea was really, okay, we can construct a state distribution of our current robot, right? So our current policy and our current robot. And we could compare it actually to the previous set distributions of historical design and policy combinations, right? So if we have seen previous designs and previous behavior, that gives us actually enough data to actually construct also like a state distribution. And then we follow really the same recipe as a co-imitation. So we can basically come up with a divergence measure, measuring the difference of our state distribution at the current design and the current behavior versus the past behavior. And the really cool thing, actually, what you can then do with that is that we don't only are limited to basically only pure imitation learning, but the idea was really like now to combine the imitation learning reward, which you see here on the left. So this is our Seil-Wasserstein distance, actually, or like the divergence measure, measuring the like how much do we actually imitate our ancestors. So hence the title of the paper. And we can combine it actually with the environment reward, right, which comes from our environment or from our human. And then Sergio actually very smartly adapted a soft actor critic to actually learn on basically two different Q functions. So one Q function which tries to learn the episodic return using the environment reward, and one episodic or like the Q function which can actually optimize or like estimate the imitation learning reward signal. Once we have these Q functions, what we can then actually do, of course, is learn our policy. And how we did it was basically learning the policy at the same time on these two different Q functions, really. And then we have like an additional parameter, like a weight parameter, which basically influences how much attention do we give to the Q function with the environment reward and how much attention do we give to the Q function for the imitation reward. The same we can actually do on the design optimization process. So we can also use here actually both Q functions. So no magic, I think it's relatively straightforward. And then the cool thing is actually what Sergio was able to show is that if we compare now this joint imitation learning and objective-driven co-adaptation process, we can really outperform the poor objective-driven co-adaptation process. So the blue line here is the classical objective-driven co-adaptation process, where you really try to only optimize for a reward. And then his cosine approach actually, where we have this combination of imitation learning signal and reward signal. And even better, so like in humanoid environment here, for example, if we actually decrease the number of episodes, so on the left side, you see humanoid trained with 1,000 episodes per design. If you now actually decrease the number of episodes we run to design per design, then actually the data efficiency really increases, and we do not really see this huge impact on it, lack of like a drop of performance by the co-adaptation process, which really uses only environmental data. Is dropping down. And this was basically like at the core of the idea. So like we wanted to basically use an imitation learning signal to counteract this distributional shift, which you have, is namely that when you go to a new design, you actually see the policy usually to drop to some level, and then it has to pick up again, and in order to recover basically the performance and find again like an optimal policy for the current design. Good. This is just a slide that we did some ablation studies. So basically, if we compared against like a number of different ablations, so basically keeping the demonstration data fixed. So in the classical causal approach, we basically update the demonstration data set throughout. So every time we actually see a better performance, we add it to our data set. And if we would not be doing this, we would still be better in terms of data efficiency, but not as good actually. And then we also compared, of course, against like a poor imitation signal. So we actually used a demonstration data set where we had like the standard humanoid, for example, or the standard walker actually reach optimal performance. And then we used that data set really to as an imitation learning signal for the co-adaptation process. Okay, yeah. So this is basically the slide I presented at the conference. So Sergio is looking for a PhD. So if you want to have a good PhD student, then let me know. I can forward you his email. But the summary is really that imitating past agents you have seen, even if they have a different morphology, can actually help you to recover from this distributional shift and increase the data efficiency of the co-adaptation process, even when you're object-driven. Now I have to go back a little bit. Yes, and with that, I'm actually at the end of my presentation today. And like a lot of thanks, of course, goes out to all the students and collaborators I had, and especially the students, Chang, Sergio, Maria, Ricardo, as well as Sylvia. I just couldn't fit her anymore in this red circle, but she should also be in the red circle again as the main contributors to this research. Yeah, and then so basically the main take-home message is that data and sample efficiency in co-adaptation is important. It's still a hard problem. We are getting closer to it, but it's still some work to do in order to really find good co-design algorithms which we can use to co-adapt robots in the real world without just doing blindly transfer learning from simulation to reality. And with that, I'm at the end of my talk, actually. So this was an advertisement I had in there, actually, for a postdoc position. So if you know anyone, let me know. But I think it closes pretty soon, actually. Cool. And now I have time for a lot of questions.
I had a quick question maybe from
Yes.
the very first part.
Okay.
So when you're talking about sim to real, are you of the opinion that like allowing the agent to modify its own morphology is actually likely to make the sim to real gap worse?
Yeah. I have this opinion. So basically, okay, so I think it's like in some limitations, it's actually worth investigating, simulation-driven co-adaptation. So I don't want to say this is like used as research or anything, right? Like it has its place, especially for robust design code or robust co-adaptation. The main problem which I found really is that if you allow the algorithm to change environmental parameters, is that you often run into this problem where the algorithm really finds the weaknesses of the simulator. So I have like in my experience, actually, which we were running like a couple of months ago, we actually had to introduce a special check for checking for flying robots, because like sometimes somehow the algorithm figures out a way actually to find design combinations where they somehow exploit the contact model of Mojoko, and then the robot gets sent flying. I'm not 100% sure how it always works, like, or how does it find these weaknesses. But of course, like a flying robot, like if it propels itself forward, is optimal. It's just not something I wanted to see. So yeah, so like the problem gets a bit harder, and basically what you need to do is really to sort of like foolproof your simulation. And then there's of course the second problem, right? So our simulators, so I know a lot of researchers and colleagues, and they spend a lot of time in engineering basically to get, for example, simulators to work better with deformable material, right? So like there's this whole research area of deformable object manipulation, and a lot of work actually goes into simulators, right? So build up these simulators. The problem is like with many of these dynamics models, they are not always perfect. So again, you run into this problem that if you have a deformable object or like a deformable like soft robot, you work often with some model, which is some approximation of the real material properties. In a perfect world, we will use finite element analysis probably to do our experiments, but even that is not 100% accurate often. So you end up again in this problem that your design, if you're really interested in optimality, right, that it actually optimizes for the simulator, but not for the real properties you may see in the lab. And then another problem, okay, so it's like a very long answer now, but like another problem is actually that, okay, in the simulator, you can construct your robot, right? So you type in your RTF, make your changes, and it pops out your robot. What it doesn't consider is like the manufacturing process itself. So if you have been using 3D printers or soft material, you know that you don't always get things super perfect, right? There are certain dynamic properties you basically induce just by manufacturing error, or like because the manufacturing process doesn't perfectly reach the theoretical implementation in the simulator. Yeah, again, I think many of these problems are currently still unsolved. We are getting closer. And I think like David's study with the cloth manipulation was especially interesting. So that's why I included it in my talk, even though it's about cloth manipulation. But it is really nice comparison between cloth simulated and cloth in the real world. And even though they found that Mojoko had the best dynamics model, so it may have improved with the newest Mojoko update, but actually it was still not perfect, right? So there was still, if you overlaid the data, there was still a difference between the textile data and the simulated textile. Yes.
If I could ask a quick follow-up. So
Yeah.
we do have some tools to like overcome the sim to real gap, like domain randomization. Do these things help when you also allow the agent to adapt its own morphology, or is it sort of more hopeless?
Honest answer is like I don't know, of course, because we haven't been doing that yet. So my answer would be yes, you may solve some problems actually. I'm not sure if you can solve all of the problems. That's probably something you would have to find out then. And I think, like I said, basically, it's like especially interesting, I think, if you're into robust control, right? Like you want to learn, let's say, a robust design, which is robust to different manufacturing errors or different environments. So my answer would be yes. So like it has, it has a place. It may help with some things. I'm not sure if it will help with everything. Yeah. So I think basically in summary, like I think both approaches are necessary, right? So we want, in a perfect world, we want to have algorithms which are capable of co-adaptation in the real world, right? Just basically informing the process using as much the real data as possible, and simulation-driven approaches for, let's say, if you want to go into an environment we know very well, right? So if we have some good idea about the environment, it's easy to build a simulator. But then, let's say, if we want to send a robot to Mars, we do not know the environment, right? It's really hard to send robots there to measure, let's say, the friction of the ground. We have some ideas, but not perfectly. Then it's really hard to build a good simulator actually to simulate these environments. Like one of the anecdotes actually which I have is with this research in the desert which we did was actually that we assumed rather naively that the desert environment actually is static, right? So like the desert environment doesn't change. I mean, I would not expect the desert necessarily to change. However, in Arizona, there's really like this unique property that the desert becomes wet once per year when the monsoon rain is coming. And we were going out, I think, in February, March or something like that. So basically just after the rain season ended. And we did experiments on 2 different days. On the first day, we learned the policy, and then on 2 days later, we actually went out again. And just for testing the setup, we re-executed the policy we learned, and then suddenly the policy didn't perform like the same. So there was like a noticeable drop in performance. And we were super lucky actually that we took like sand samples, and then basically we figured out that the humidity dropped in the sand, right? So the density changed, which in retrospective makes sense, but we would not have considered it at all during the learning experience if we would not have taken samples actually. And I think that's also like really important to consider actually that we sometimes think we have really good ideas about the environmental variables. In our lab, especially, we know we can control the environmental variables. But I mean, at the end of the day, we don't want our robots to be stuck in the lab, right? So we want our robots to actually leave the lab and do tasks in the outside environment. And in the outside environment, we often actually don't have a good idea of what's going on, right? So the robot has to deal with what's given to it or in the environment in which it's moving. And then you have 2 questions. Are you interested in optimal control or in robust control? And I think robust control, like for example, like changing dynamics parameters in simulation gives you, like, I think to some extent this robust control. But if you want to optimize our robots, for example, for optimality, really like energy efficiency, right? So especially mobile robots, they need to get the maximum performance out given their battery life. Then we are really interested in having robots closely adapt to the environment. So like really doing this niching. So that's what we're going into. Okay. Now I'm at the end of my answer.
You have a question, Audrey?
Yeah, I do. My question is about multimodality and your co-adaptation framework that you've shown here. So you motivate this whole thing with like a picture of a turtle. A cool thing about a turtle is it can crawl through sand, and it can swim. Obviously it's really hard to co-optimize a design that can be multimodal. I think that's like still a pretty open thing. But I'm curious, like for the framework you presented here, how would you put in multiple behaviors without having the same problem that you said, where a person has to just like put in reward functions that indicate that there's going to be multiple behaviors?
Oh wait, which work were you now talking about? The classical co-adaptation or the one with using imitation learning?
The one with using imitation learning. Maybe the classical one could do it though. I didn't think that hard about the question.
Yeah, because in the classical one, I would say it's basically just you extend the, you would basically go back to the contextual markup for decision process, right? So if you know there's a change in task, then you can encode that, I assume.
Okay.
Like, really interesting question, I think, is probably like, what do you What if you don't know did a task change, right? So what if you have to infer this from data, right? This meta learning driven approach. So
you find out that the dirt is wet, or you find out that now you're in the water. Yeah.
Yeah. That's tricky. Yeah, that's a good research problem. So I don't have a clear answer for that. So like, I mean, there are probably like, I can speculate what I would do. Having a sample maybe of different reward functions learned from data, maybe that. Like basically doing something similar to what we did with measuring the internal Wasserstein distances between demonstrations, right? I think that may be a good approach.
Yeah. I have one more, unless Adriana wants to go first, maybe.
Maybe also just to add with the turtles, actually. So the idea was also like we were looking at baby turtles. And the reason for that is basically because they have to move super fast when they get born.
To not get eaten. Okay.
Exactly. Yeah.
I'll ask mine afterwards, my other question.
My question is actually about the imitation learning as well. So I just wanted to sort of ask a clarification question. You mentioned that you're using adversarial imitation learning, but maybe I missed what the adversarial part was. Are you explicitly learning a reward function, or?
Yeah. So basically the adversarial imitation learning, I super collapsed into the reward function, right? So
it's just Gale.
Yeah, it's basically, so you know Gale. If you know Gale, then basically you almost know Sale. So there's not a super large difference between them, other than that state alignment imitation learning. So that's what we use. I use Sale. The main difference is that you really only operate on the states.
Okay, so I guess I'm curious, like adversarial imitation learning, I think can be sort of unstable or difficult to train. So, and now you're adding this additional optimization layer of the morphology optimization. So I guess I'm just curious if this was hard to get working, or how difficult it was to actually train this.
Yes, it was very difficult. So I'm laughing because actually Chang, right? Like, so this poor guy actually did. So Chang here actually, so he's now a postdoc in Switzerland. So he came to our lab in Helsinki. Actually, he was like, "Oh, I'm going to do a 6 month visit here. I want to do like a cool project." And I was like, "Oh, invitation like for co-adaptation." If he would have known what would have happened, maybe he would have reconsidered, because actually it was a very long project. So we were able to manage to get it to work, but it took a lot of time. So for example, we initially started actually with like approaches like Gale, but then very quickly we figured out like they didn't really work very well for us. And then the whole training setup, like it was hard. Yeah. So in short, yes, it was very hard. Yeah, cool. You could probably ask Chang more. Like he had to go through it. We had the meetings and the discussions in the code, but like yeah.
Gotcha. Okay, thanks.
Is there time for one more question or no?
Go ahead, Charlie.
I mean, Audrey can go. I think she was cute.
Oh, I didn't see you. Sorry, you're very tiny. I think Charlie should go.
I'm sort of curious to, by the way, see you again. Nice to talk again. But I'm curious to hear your thoughts on how to deal with the adaptation of morphologies when the action and observation spaces are incompatible. Like, is it really a different problem than just adapting? The same spaces? Like, does it change? Is it?
Maybe to clarify, do you mean in the sense they change because you change the dimensionality of your problem, like you add motors, or do you mean that even if you keep the dimensionality same, the action spaces itself basically change the meaning? Or
yeah, basically, if you adapt your morphologies and you add actuators, you add sensors, yeah.
And then your question was, sorry?
Versus just like changing the length of certain limbs for one morphology, as you can in these, like for example, for the humanoid, where you just change the length of the limbs. Like, are these two problems like very different? Are they the same? Can you deal with them with the same method?
So for the same methods, like, so you can deal with the same methods if you assume there's an upper limit, right? So basically, if somehow you can assume you don't have more than X motors, then I think like using standard MLP basically, or like using image data maybe as input or something like that actually works, right? So like there are some works, I think, with soft robots where they use just an image representation of the state of the robot, and then that actually works. If the topology so if the graph structure really changes, then things of course become more tricky. Then I think actually you either need to use a GNN, like a graph neural network, or like, one of the transformer-based approaches. Yeah, it depends. So the problems in themselves can be very different. And also harder, right? So like if you actually consider changing the graph structure of the robot, you may not, I'm wondering if you get away with, yeah, you probably have to explore many more different variations of your robot. So like say the data efficiency probably goes lower, right? So you need more training data. You need to see enough graph variations actually in order to get a feeling of what is a good graph to explore next. So I think the complexity increases, even though if you look at design variables in a real numbered space, right? That's what we're looking. If you have 8 dimensions, you still have a super large area to cover, right? But in that sense, maybe, yeah, I'm not sure. Yeah. So you may make your problem a bit more trickier. I mean, the biggest thing which really changes, I would say, is that actually the training time increases to the burst, right? So many of the experiments are short. They basically run often 3 to 4 days, right? Even if you have the computer by yourself and you have like a high frequency CPU, the experiments actually often take 3-4 days. The more networks you train, the worse it becomes. And then GNNs, I found, like in this one paper, we're actually increasing the time even more because you have to do this message passing approach. So maybe due to the learning algorithm, it becomes even worse. Yeah.
I see.
So if you want to get started, I would say if you want to get started, maybe first check out the fixed sized design spaces. I mean, many of them actually are enough to investigate these general questions about, like, for example, like, oh, does imitation learning actually help for co-adaptation or not? Before you go to the graph-based approaches. Although the graph-based approaches, you can have like a lot of different nice forms. And then also for the graph-based approaches, you have 2 decisions you can make. Do you allow changes to the links or do you not allow changes to the links? So for example, if you go to RSS, happened last week, so the Robotic Science and Systems Conference, I think there were some colleagues actually who presented an approach with robots which were made out of basically like a graph. So you had like connecting elements and nodes. And I think the connecting elements actually didn't change the length at all. So like the length was always fixed. And the question was really like, okay, how do we find the perfect combination or like this perfect graph basically to move forward. So like there's also this flavor actually where you don't change the material or the sizes or
Yeah, interesting. Cool. Thank you.
If there aren't any more questions, I think we can wrap up for today. Thank you very much for the talk, Kevin.
Good. Awesome. Thanks so much for the invitation.
Hope to see you soon.
All right, thank you.
Thanks,
Bye.
Kevin.
See ya.
Take care.
Let's push the button. I think so. It's still recording. Yeah.